Hello students, I hope you're having a great day. So today I would like to take a look at one of the practice problems in Chapter 5 over kinetic friction. And this is number 4 on the worksheet, the playing card problem. So what I'm going to do is I'm going to complete the problem with you step by step. So I'm first going to read the problem, I'm going to underline important information, then I'm going to generate a column of knowns and unknowns. So let's go ahead and get started. John is playing cards with his friends and it is his turn to deal. A card has a mass of 2.65 grams and it slides 0.4 meters along the table before it stops. If the coefficient of kinetic friction between the card and the table is 0.21, what is the initial speed of the card as it left John's hand? So the problem is telling us that the card slides on the table and it comes to a stop. So let's go ahead and generate a column of knowns and unknowns. So the mass of the card is 2.65 grams. The final displacement of the card, identified by d sub f, is 0.4 meters. And the card comes to a stop. So the final velocity of the card is 0 meters per second. If the coefficient of kinetic friction between the card and the table is 0.21, what is the initial speed of the card? So the initial speed is what we are going to calculate. That is our goal. The first thing I would like to do is go ahead and convert the mass of the playing card from units of grams to units of kilograms. Now we can perform dimensional analysis here, and so we're going to multiply by a ratio that eliminates the unit of grams, and we're going to multiply by 1 kilogram divided by 1,000 grams, because we know that 1,000 grams equals 1 kilogram. So right here, this can be grams over 1 algebraically. So I have a gram in my numerator and a gram in my denominator, so those will cancel. So when I divide 2.65 by 1,000, we're going to move the decimal place 3 places to the left, and this is going to give me 0.00265 kilograms. Okay? The next thing we need to do is draw a picture to really describe what's going on. So if I have a playing card here, and it's sliding on the table, it has an initial velocity, but it comes to a stop. So my final velocity is equal to 0 meters per second. Now we know that the card's displacement is 0.4 meters. So I'm going to draw this, identify my displacement with d sub f. This is 0.4 meters. Okay, the next thing that I need to do is draw a free body diagram. Okay, so on a free body diagram, we're first going to show the weight force due to gravity, identified by F sub g. Now we are not given the weight force due to gravity, so we need to calculate it. We are given the object's mass, and we know that the weight force is equal to the product of the object's mass and the acceleration due to gravity. So the mass, we have this in kilograms, it must be in kilograms, 0.00265 kilograms, multiplied by negative 9.8 meters per second squared. Okay, so everyone needs to take out their calculator. And we get negative. So we have a vector arrow pointing in the negative y direction, because we know that weight force due to gravity is applied in a negative y direction. This is negative 0.02597 newtons. So we have kilogram meters per second squared. and we know that equals 1 Newton. Now, looking at the simple picture that we drew, we know that the card is in equilibrium in the y direction. So that means that the normal force that the table is applying to the card is equal in magnitude to the weight force due to gravity, but the vector is pointing in the opposite direction. So we have an interaction pair here, 0.02597 newtons. Now, the only other force acting on the card is the force due to kinetic friction. And this is identified by F sub F sub kinetic. And it's kinetic friction force because the card is sliding. Now, as soon as John throws the card and it's sliding on the table, there is no more force being applied to it in a positive x direction. The force in the x direction, which is opposing motion, is in the negative x direction, and it's the force due to kinetic friction. So what we need to do is calculate the kinetic friction force right now. Now we're going to start with the equation from the book, and our equation is the kinetic coefficient of friction is equal to the kinetic friction force divided by the normal force applied to the object. So we have this was given to us in our problem, which is 0.21, and we've calculated the normal force. We did that in the free body diagram. So we need to isolate kinetic friction force, and how we're going to do that is multiply by normal force on both sides of the equal sign. On the right hand side, normal force cancels. So this gives us kinetic friction force is equal to the product of the coefficient of kinetic friction and the normal force applied to the object. So what we have here is 0.21 times my normal force, 0.02597 newtons, and we get 0.005454 newtons. Okay? Now, this is a force, so it is a vector. We need to take a look at our free body diagram here. And our vector here is opposing motion, so the kinetic friction force is pointing in a negative x direction. So let's go ahead and fill in that value. And we have units of newtons, so please do not forget to put your units of newtons on there. Okay, now that we know this, we need to identify the net force in the x direction. Well, we know that F net in the x direction is equal to the sum of the forces in the x direction. Well, we only have one force here, and it's pointing in the negative x direction. So the net force applied to the card is going to be a negative, and this is in the x direction, negative 0.005454 newtons. And since we know the net force applied to the object, we can calculate the object's acceleration. And remember that the acceleration vector and the net force vector are always going to point in the same direction. So we can use Newton's second law of motion here. It tells us that the acceleration of an object is directly proportional to the net force applied to the object and inversely proportional to the object's mass. So F net divided by mass. The net force, you have that right here, a negative 0.005454 newtons divided by the mass of the object, and you calculated that earlier with units of kilograms. So 0.00265 kilograms. So our acceleration is negative 2.058 meters per second squared, okay? And this makes sense with a negative acceleration because when John throws the card has a positive velocity, and since the net force vector is pointing in a negative x direction, we know that the acceleration vector will also point in the negative x direction. So it's going to slow the card down until it comes to a stop. And we know that the displacement of the card when it slides on the table is 0.4 meters. So to calculate our initial velocity here, we're going to use the equation final velocity squared is equal to initial velocity squared plus 2 times our acceleration times the displacement of the object. So what we're going to do is isolate initial velocity squared, and we're going to do that by subtracting 2a d sub f from both sides of the equal sign. So this is going to give us initial velocity squared is equal to final velocity squared minus 2 times acceleration times our final displacement. Now the final velocity of the card, we already know it's 0, so we don't need to mess with it anymore because this goes to 0, and we know 0 squared is 0. So our initial velocity squared is equal to negative 2 multiplied by our acceleration, which is a negative 2.058, multiplied by the displacement of the card, which is 0.4 meters. So let's multiply all this out, and I get a positive 1.6464. Okay? Now let's take a look at the units here. I have meters per second squared times meters. And algebraically, we know that meters is meters over 1. So meters times meters, in my numerator, we have meters squared. So my units are meters squared per second squared. But we're not finished here, because look at this. We have initial velocity squared. To eliminate that square, we need to take the square root. And remember the old algebra rule. To keep this balanced, what we do to one side, we have to do to the other side. So we also have to take the square root here. On the left-hand side, we know that taking the square root of a squared value, it will just be that value. So those cancel each other out. So initial velocity is equal to, let's talk about the numerical value first. .283. Now remember, not only are we taking the square root of the numerical value, we are also taking the square root of the unit value. So the square root of meters squared per second squared is just meters per second. And this checks out because remember, velocity is a vector. And when we set the problem up, we have an initial velocity moving in a positive x direction. Remember, it is a vector, so the positive sign does show it has a positive velocity initially. So I hope this has helped you with the problem. If you have any questions, please feel free to give me a call, send me an email, or contact me on Canvas. I hope you have a wonderful day.